The increasing demand for electricity and the growing complexity of power transmission networks have created significant challenges in maintaining power quality and system stability. One of the critical issues in modern power systems is the management of reactive power, which is essential for maintaining voltage levels and ensuring efficient power transmission. Reactive power compensation has become increasingly important as transmission lines are loaded closer to their thermal limits, and as the integration of renewable energy sources introduces additional variability to the grid. Reactive power is a necessary component of AC power systems that supports the magnetic fields required for inductive equipment to operate. Unlike active power, measured in watts, which performs actual work, reactive power, measured in VARs, oscillates between source and load without producing net energy transfer. The relationship between active power, P, reactive power, Q, and apparent power, S, is represented by the power triangle, whereas superscript 2 equals P superscript 2 plus Q superscript 2 and the power factor is the cosine of the angle between P and S. Poor power factor results in increased current flow for the same amount of active power transfer, leading to higher losses and reduced system capacity. Flexible AC transmission systems, FACS, represent a revolutionary approach to enhancing the controllability and power transfer capability of AC transmission systems. FACS devices are power electronic-based systems that provide control of one or more AC transmission system parameters. These devices can be classified into two generations. First-generation devices like static VR compensators, SVCs, and second-generation devices like static synchronous compensators, STATCOMs. Both SVC and STATCOM are shunt-connected FACS controllers designed to provide reactive power support to improve voltage regulation and system stability. The need for reactive power compensation arises from several factors. First, as transmission lines become more heavily loaded, voltage drops increase, potentially leading to voltage collapse if not properly managed. Second, modern power systems must accommodate a wide range of load types, many of which have poor power factors and contribute to voltage instability. Third, the integration of renewable energy sources, which are often intermittent and located far from load centers, creates additional challenges for voltage management. Reactive power compensation devices help address these issues by providing dynamic support to maintain voltage levels within acceptable limits. Static VR compensators, SVCs, are first-generation FACS devices that have been widely used in power systems for reactive power compensation. An SVC typically consists of a combination of thyristor-switched capacitors, TSCs, and thyristor-controlled reactors, TCRs, connected in shunt with the transmission system. The basic principle of SVC operation is to vary the reactive power output by controlling the effective impedance of the device. When the system voltage is low, the SVC supplies reactive power by switching in capacitors. When the voltage is high, it absorbs reactive power by increasing the conduction angle of the TCRs. The configuration of an SVC generally includes a fixed capacitor bank, a thyristor-controlled reactor, and a control system that monitors system voltage and adjusts the reactive power output accordingly. The control system typically uses a voltage regulator that compares the measured system voltage with a reference value and generates a control signal to adjust the firing angle of the thyristors in the TCR. This adjustment changes the effective reactance of the TCR, thereby controlling the reactive power exchange between the SVC and the power system. One limitation of SVCs is that their reactive power output is dependent on the system voltage. The reactive power supplied by an SVC is proportional to the square of the system voltage. Q is proportional to V superscript 2, which means that during low voltage conditions, when reactive power support is most needed, the SVC's capability is reduced. Additionally, SVCs typically require large inductors and capacitors, resulting in a significant physical footprint and relatively slow response time compared to more modern solutions. Static synchronous compensators, STATCOMs, represent the second generation of shunt-connected FACS devices and offer several advantages over SVCs. A STATCOM is based on a voltage source converter, VSC, that uses power electronic switches, typically IGBTs or GTOs, to generate a controllable AC voltage from a DC energy storage element, usually a capacitor. This AC voltage is coupled to the power system through a transformer, and the reactive power exchange is controlled by adjusting the magnitude and phase of the generated voltage relative to the system voltage. The principle of STATCOM operation is fundamentally different from that of an SVC. Instead of varying impedance, a STATCOM acts as a controllable voltage source that can generate or absorb reactive power by controlling the voltage difference across the coupling transformer. When the STATCOM's output voltage is higher than the system voltage, it supplies reactive power to the system. When it is lower, it absorbs reactive power. The reactive power output of a STATCOM is directly proportional to the system voltage. Q is proportional to V, rather than the square of the voltage as in an SVC. This voltage-independent characteristic of STATCOMs provides a significant advantage during low-voltage conditions, as they can maintain their full reactive current capability even when the system voltage drops. Additionally, STATCOMs typically have faster response times, often less than 1 cycle, compared to SVCs, typically 1 to 2 cycles, making them more effective in mitigating rapid voltage fluctuations and improving transient stability. The VSC-based topology also allows for more precise control of reactive power and can be designed to have a smaller physical footprint than equivalent SVCs. The comparative analysis between SVC and STATCOM reveals several key differences in performance characteristics, operational capabilities, and application suitability. One of the most significant distinctions is the voltage current, VI, characteristic of each device. An SVC exhibits a drooping VI characteristic, meaning that as the system voltage decreases, its reactive current capability also decreases. In contrast, a STATCOM maintains a relatively constant reactive current capability over a wide voltage range, providing superior performance during voltage sags and other disturbances. From a technical perspective, STATCOMs offer several advantages over SVCs. Their faster response time enables more effective mitigation of rapid voltage fluctuations and better support during transient events. The voltage-independent reactive current capability ensures full performance during low-voltage conditions, which is critical for preventing voltage collapse. Additionally, STATCOMs typically generate higher-order harmonics that are easier to filter than the lower-order harmonics produced by SVCs. The compact design of STATCOMs also results in a smaller physical footprint, which can be advantageous in space-constrained installations. However, these technical advantages come at a cost. STATCOMs are generally more expensive than SVCs due to the more complex power electronics required for the VSC topology. The initial capital cost of a STATCOM can be significantly higher than that of an equivalent SVC, which may be a determining factor in some applications. Additionally, the control systems for STATCOMs are more complex, potentially requiring more sophisticated maintenance and technical expertise. The choice between SVC and STATCOM depends on various factors, including the specific application requirements, system conditions, and economic considerations. For applications where rapid response and full performance during low voltage conditions are critical, such as in weak grids or systems with high penetration of renewable energy, STATCOMs may be the preferred solution despite their higher cost. For more stable systems with less stringent performance requirements, SVCs may provide a cost-effective solution for reactive power compensation. Simulation studies using MATLAB/Simulink have demonstrated the superior performance of STATCOMs in various scenarios, including load variations, voltage disturbances, and fault conditions. These studies show that STATCOMs provide better voltage regulation, faster response to system changes, and improved transient stability compared to SVCs. The voltage-independent characteristic of STATCOMs is particularly valuable during severe voltage dips, where they can maintain full reactive current support while SVC capability is significantly reduced. In conclusion, both SVC and STATCOM are effective solutions for reactive power compensation in power transmission systems, but they offer different performance characteristics and cost profiles. STATCOMs, as second-generation fax devices, provide superior technical performance with faster response times, voltage-independent operation, and better performance during system disturbances. However, these advantages come at a higher initial cost. The choice between these technologies should be based on a careful evaluation of the specific system requirements, performance needs, and economic constraints. As power systems continue to evolve with increasing complexity and higher penetration of renewable energy sources, the advanced capabilities of STATCOMs are likely to become increasingly valuable for maintaining system stability and power quality.